In this problem, we're removing methylcyclohexane from N-heptane, aniline as a solvent, and with a feed of 200 kilograms per hour with composition. So the first part is to look at the outlet streams with a single stage, so a single mixer settler. I have the equilibrium data here. So obviously the first thing we're going to do is just write out these streams. Have our feed and our solvent, and the flow rate we're going to add here in kilograms per hour. It's just put the column there. And so our feed is 200 kilograms per hour, and the solvent is 600 kilograms per hour. And then after that, the composition. So we have first have aniline, then we have methylcyclohexane, and finally we have N-heptane. And let me adjust this here. Perfect. So aniline is 0.05 in the feed. The cyclohexane is 40%, and the N-heptane is 55%. And then for the solvent, we have 95% aniline, 0% methylcyclohexane, and 5% N-heptane. Perfect. Now let's go ahead and draw the equilibrium diagram. So let's create a scatter plot here, and then let's select our data. And for the x-axis, we're going to choose N-heptane, and for the y-axis, we're going to choose methylcyclohexane. And this gives us something like this. And this is the x graph. And then we're going to add another series and do the raffinate. So we get this graph here, and I'm just going to draw some lines. One thing we've noticed is that this does not look like the typical ternary phase diagram. It is not a closed envelope, but that's fine. That just means that the two phases never really become similar, so they're always in two separate phases. But otherwise, the problem is completely identical. Alright, so now we've drawn our tie lines. So something you may have noticed is that all the tie lines here are bunched really closely together, which just goes to show how important it is to really precisely draw your tie lines. In this case, if we're using Excel, it's a little easier, but in any case, regardless of what medium you're using to draw your graphs, precision is key. Now, the next step, as always, is to calculate the mixing point. So, for the endpoint. Endpoint, as we all know, is simply what happens when you take the feed and the solvent and you mix them together. So the flow rate would be equal to the feed plus the solvent, and then the composition would be the resulting composition. So we have to take the weighted average of the two compositions be equal to solvent flow rate times its composition plus feed flow rate times its composition divided by the total flow rate. And we can repeat this. Now that we've calculated the mixing point composition, we can go ahead and trace our line between the streams and the mixing point. And just to make things a bit easier, I've gone ahead and divided all of the equilibrium concentrations by 100, and this simply gives us the full fraction instead of the percentage. So to do that, it's quite simple. You just simply plot the methylcyclohexane versus the N-heptane. Well, methylcyclohexane is X is the y-axis, and N-heptane is the x-axis. So if we've done this correctly, then these 3 points should be collinear. And they are, which means that we did our job right. So the mixing point is this point here, and this means that equilibrium line can now be traced. Looks like it's something like this. So that is composition of our outlet streams, and if we look closely, looks to me, and we can actually add some grid points. So the extract stream is going to be the stream on this side, and the raffinate stream is going to be the stream on this side. So if we look closely, looks to me that the raffinate stream is approximately at the point 0.32 and 0.6. So composition would be represent methyl cyclohexane. Methyl cyclohexane is y-axis, so this would be 0.32. And the N-heptane would be about 0.6. On the other hand, it's approximately 0.05 and 0.38. 0.03. So we can count the aniline because it's simply 1 minus the composition. Okay, now we need to calculate the flow rate for the extract and the raffinate. So if we write out the mass balances, we have the component mass balance for any specific component, as well as the overall mass balance for the extract, raffinate, and the mixing point. Do a little bit of algebra, we'll find that the raffinate flow rate is equal to mixing composition times the mixing flow rate minus the extract flow composition times the mixing flow rate divided by the difference between the raffinate and extract composition. Let's do that. This gives us 179.8 grams per hour. And the extract flow rate is 6 minus the raffinate. And there we have it. So 620 kilograms per hour. And that's it. That is it for problem 1. Now for problem 2, they're asking us to use a 2-stage cross-flow system with 300 kilograms of solvent. Okay, so we're basically taking this solvent stream and we're dividing it in half, and then we're using 2 stages instead of 1. So what will this look like? So first of all, let's just create another section for the second part of the problem. And this time the compositions are the same, it's just that the solvent is now 300 kilograms per hour. Now the mixing, so the procedure is completely the same, so we can just go ahead and calculate the mixing point. So it is going to be equal to this plus this, and then and the composition is once again a weighted average. This solid flow rate plus feed composition times feed flow rate divided by brackets divided by total, and it's constant, and then higher all of the. There we go. And now what we can do is we can create a new graph here. Next step is to simply graph the point. And once again, since the compositions of the feed and the solvent are the same, we should expect this mixing line to be the same. It's just that since flow rates are different, the mixing point will be at a different point. once again, using the X values as N-heptane and the Y values as methylcyclohexane, get virtually the same thing, except that the mixing point is now. So from here we can tell that this mixing point is roughly along this tie line here, and so let's just use that one for convenience. So now we have first extract stream and the first raffinate stream, and in terms of the equilibrium, you can actually just consult. So looking at this graph, it looks like the correct point to choose is here. So that means that our extract stream has a composition of 4.6% methylcyclohexane and 4.5% heptane. So let's go ahead and write that. And then for the raffinate, it looks like we're at 33.8% methylcyclohexane and 57.6% N-heptane. Aniline is obviously just to 1 minus the other two compositions. Once again, we can calculate the flow rate using the same as before. And now we have a flow rate of 193.8 kilograms per hour. Then extract is obviously just 500 minus the raffinate. That gives us a flow rate of 306 grams per hour. So that was for the first stage. Now for the second stage, we're going to have another mixing point once again, and we're going to use the raffinate stream. So the raffinate stream, obviously, a stream that is being purified. So we're going to keep it, and we're going to use another solvent stream, which is functionally identical to this stream. M2 is equal to the combination of two streams. And then the composition, once again, weighted average. Once again, we can plot the new line. Once again, this should be collinear, and it is. Okay, so now I've drawn the equilibrium line, and I simply have to take the composition and plug them in. So here, it looks like the N-heptane composition is about 62%, and the methylcyclohexane percentage about 29%. Over here, it's a bit harder to tell. I would say it's about 3.7% methylcyclohexane and about 4.4% N-heptane. Right, E2 and R2 for the second extract and raffinate streams. So for the extract stream, I would say, again, this was 0.038, 0.04, and then in terms of methylcyclohexane, this was about 9, and now the flow rate, once again, is calculated the exact same way. So let's go ahead and do that. There we have it. That is our final composition action. So we're done. Just keep in mind that you need to be very precise with your tie lines, or else you are going to get a completely different result.